Hello everyone. We are pleased to present the outcome of our internship work, and I am Devi Krishnais. The internship journey began with foundational concepts in programming languages, specifically C and C++. Programming languages can be classified by their proximity to hardware, portability, and level of abstraction. And here is our breakdown. High-level languages. These include Python, Java, and C++. They are designed to be independent of specific hardware, more expressive and more abstract, which tends to make them more portable across platforms. Then comes to the middle level language. C is often called a level language. It combines features of high level languages like expressiveness and portability with low level features like direct memory access, pointers, making it efficient and hardware aware. Then the third point is low level language. Assembly language falls in this category, which is very efficient, close to hardware, but not portable and much more difficult to write and maintain. Because of its features, C can be used in development of embedded systems, software, OS, middleware, firmware, and file systems. Now, let's list key features of C. General purpose. It isn't designed only for one domain, but usable across domains. Then, free formatted. The syntax is flexible, statements separated by semicolons, and code blocks via braces. Rich library access. Extensive standard libraries plus user-defined libraries. Then comes the portability. C programs can be run on different platforms with minimal modification. Structured or modular programming support. Uses of functions, control structures, blocks are the features of C. Now let's look at the key features of C++. First one is statically typed and compiled. The type of each variable is known at compile time. Code is compiled to machine code. Next comes the general purpose. C++ can be used for many kinds of applications, system software, application software, games, real-time systems. They are case sensitive. Upper versus lowercase identifiers are distinct. Object-oriented. Supports classes, objects, encapsulation, inheritance, polymorphism, data abstraction, and data hiding. Superset of C. Most legal C programs are legal C++ programs, and C++ builds upon C's features. High performance and control over memory and hardware. Since C++ retains low-level capabilities while offering higher abstractions. When working in C or C++, you will encounter many general programming concepts, and we are going to summarize some of them here. Keywords in C. Words reserved by the language, like int, if, return, struct, etc. Code structure. The typical structure of a C program. Headers, main function, declarations, definitions, and statements. Number system, binary, decimal, hexadecimal, and their representation in code. Signed and unsigned. Numerical types may be signed, like positive and negative, or unsigned, in any only non-negative values, like. The next type is data types, int, char, float, double, etc. Size and sign modifiers. Then comes conditional statements like if, else, switch. Arithmetic operators, logical operators, bitwise operators, relational operators, array. An array is a collection of elements of same type, contiguous memory allocation. Function, modular units of code, definition call, parameter passing. Pointers for variables storing memory addresses, pointer arithmetic, dereferencing used in dynamic memory, and endian representation, the order of bytes in memory, which can affect portability. Pass by value and references. In C, by default, parameters are passed by values. To stimulate pass by reference, you can use pointers. OOPS concept. When you switch to C++, you will deal with object-oriented programming, which includes classes, objects, methods, inheritance, polymorphism, etc. Access specifiers in C++. Public, protected, private to govern access of class members in the code. We will move on to the next slide. Now, I will take you through the requirements of our internship project titled Home Automation using Arduino, Blynk App, and PICSimLab Simulator. Our goal is to control light, temperature, and water tank level in a home environment context. I will break down each requirement in turn. Our first requirement, garden light control. We will use an LDR, light dependent resistor sensor to measure ambient light level. Based on the LDR reading, the brightness of the garden lights will be adjusted automatically. For example, when it gets dark, lights turn on, and when ambient light is sufficient, lights dim or switch off. While implementing, we will need to map sensor values to brightness levels via pulse width modulation control of the lighting circuit. Our second requirement is temperature control system. A temperature sensor, specifically the LM35, is used to measure ambient temperature. This sensor gives an analog voltage proportional to temperature. The measured temperature is displayed on a character LCD through serial communication or direct interface. Based on the temperature reading, the system will automatically turn on a heater or cooler when the temperature is outside a predefined threshold. Our third requirement comes to water level control. The goal is to monitor the water volume in a tank, displaying the current value on the CLCD and control inlet or outlet valves based on the volume. For example, if the tank level falls below a lower threshold, open the inlet valve, and if it exceeds an upper threshold, close the inlet valve or open the outlet valve. For this, serial tank tool of PICSimLab is used. The serial display prints the measured volume or level so that the users can see real-time status. This subsystems adds automation to water management, avoid overfilling, avoids running dry, or provides monitoring.
Hello everyone, I am Drishya. After the project requirement, we are moving on to what we studied about IoT and embedded system. The Internet of Things refers to connecting physical devices such as sensors, actuators, machines, etc. to the Internet so that they can collect, send, receive, monitor, and act on data remotely. These capabilities allow IoT systems to deliver both comfort and potentially life saving applications. The applications span many domains like agriculture, transport, factories, predictive maintenance, medical, smart cities, etc. Here is how IoT architecture are typically layered. The first layer includes the sensing layer, where devices like sensors, actuators that interface with the physical world. The next layer is the connectivity layer or the communication layer. This layer handles the connectivity between the device and the rest of the system through the wired, wireless protocols and gateways. The next layer is the data processing layer, which is responsible for storage, processing, analysis of data from device. This may include edge computing, cloud, and analytics. The next layer is presentation layer. It interfaces and use cases such as mobile apps, dashboards, automation system for end users. Next, we are going to look what is embedded system. An embedded system is a combination of hardware and software designed for a specific task or function. Examples: digital watches, washing machine, microwave oven, industrial controllers, automatic control units, etc. Embedded system can be classified in many ways. One is standalone system. This may be of two types. One is the slave following the order of the master blindly, like a semi-washing machine, or it taking the decision on its own, like a self-driving car. Next one is real-time embedded system, where the task should be completed within the deadline, like airbag systems in vehicles. The next one is mobile embedded system, which is portable like smartwatch. Other embedded systems includes hybrid and network embedded system. An embedded system typically comprises several essential components. The brain of the embedded system is the processor or the microcontroller. Next part is the memory, which can be program memory or data memory. Memory is of two types, RAM and ROM. In RAM, read and write can be performed infinite time, but in ROM, read can be performed infinite times, but write can be performed only once. There are more hybrid memories like EEPROM, flash, etc. The next component is input-output interfaces like sensors, actuators, displays, user interface, etc. The next component is communication interface and peripherals like wired and wireless communication protocols like UART, SPI, I2C, Ethernet, Wi-Fi, Bluetooth, etc. Next, we look into the tools that we have used in this internship. First of all, Arduino IDE. Arduino IDE is an open source software used for writing, compiling, and uploading code to official Arduino boards and other compatible microcontrollers. Programs written in the IDE, referred to as sketches, use a language similar to C and C++ and are saved with the .ini file extension. There exist two types of systems. One is host, which is used to develop the target. The next system is target, which is being developed to do a specific task. For example, Arduino Uno is a target system on which code is being deployed, and our laptop is the host on which the programming is done. Next, the tool is PICSimLab Simulator. It is a real-time open-source emulator for microcontrollers that allows users to simulate the interaction between a microcontroller and peripheral components, making it a valuable tool for learning embedded systems, programming, and hardware prototyping without physical hardware. It is primarily designed for the PIC board family. It also supports Arduino ESP32 and Raspberry Pi Pico boards. It simulates an entire hardware environment including the MCU, LCD displays, sensors, motors, serial communication including UART, I2C, SPI and various input-output components. When we are working with PICSimLab Simulator, the code has been written in the Arduino IDE is exported as .hex file and it is loaded in the PICSimLab Simulator. Next, we are going to see what we done with the LED. The first hands-on experiment was done on the LED. Many Arduino boards have an inbuilt LED connected to the digital pin 13. By default, we can simply set the pin 13 as an output and drive it high or low to turn the LED on or off. If we use an external LED, connect the LED to any digital pin of the Arduino and the negative to the ground. In the code, define that digital pin, set it as output in the setup and write high or low in the loop. Here are the main functions that we will use when programming in Arduino IDE. First one is pin mode. It sets the specified pin to act as an output or input. Next one is digital read. It reads the state like high or low of a specified digital pin that has been configured as input. Next one is digital write function. It writes a high or low value to a pin configured as output. Next function is delay. It causes the program to pause for a specified number of milliseconds. It is useful for creating visible delay between turning LED on or off while making the program for blinking an LED. Next, we learned about the ADC. Why we need an ADC? Sensors often output an analog voltage, but microcontrollers work with digital signals. Therefore, the analog output from a sensor must be converted into a digital value for the MCU to read. That conversion is performed by an ADC, analog to digital converter. The conversion process can be broken down into major steps. First step is sampling, where the continuous analog voltage is sampled at periodic intervals in time. This yields discrete time snapshots of the analog signals. Next step is condensation. The amplitude of each sampled value is mapped to the nearest one of a discrete set of levels. The number of levels depends on the resolution of the ADC. The last step is encoding or digital encoding. Each condensed level is represented by a binary code which the digital system can use. If we are having an 8-bit ADC, the digital value range from 0 to 255. For the Arduino, The built-in ADC is 10-bit resolution. So the digital output ranges from the values 0 to 1023. There are several ADC architecture, each with trade-offs in speed, resolution, cost, power. Some common types includes flash ADC, SAR ADC, that are common in MCUs, dual slope ADC, and pipelined ADC. Some ADC key parameters includes resolution, which is nothing but the register width of the ADC. Next is the acquisition time. It is the time that ADC takes to sample and hold the analog output before conversion begins. Next parameter is the conversion time. That is the time required for the ADC to convert the sampled and held value into the digital code. Here are two main analog functions that we use when working with Arduino IDE. One is analog read, that reads the analog value on the specified analog input pin and returns a digital integer. Next one is analog write, writes an analog value to a pin that is specified within the function.
Hello everyone, I am Abhidami AR. In this part, I will explain how we program a character LCD, that is CLCD, specifically a 16x2 display connected via the liquid crystal underscore I2C library. The CLCD is used to display reading values and ASCII characters on your device. In our automation system, we need a simple display to show sensor data. Using a 16x2 LCD gives us two lines of text, 16 characters each, for enough for key information without complex graphics. Because we can use an I2C module because the wiring is minimal, just SDA, SCL, power, and ground. And the control is much simpler than a full parallel interface. We use Liquid Crystal I2C library for Arduino, which is included in the code and initialized as Liquid Crystal underscore I2C space LCD of address, column, and rows. In setup, we typically use the functions like lcd.init, lcd.backlight, if the backlight control supported. Some libraries use lcd.begin instead of init. And the column parameter is the number of characters per line. Rows is the number of lines. In our case, 2 for 16x2. Here are some main functions we will use when working with LCD. lcd.setCursor of call row. Move the cursor to the given column and row 0 based before printing. lcd.init or lcd.begin initialize the LCD for the use. lcd.clear clears all text from the display and optionally reset cursor to home position. lcd.print of value prints a string, character, or number at the current cursor position. Additional functions, depending on the library version, may use lcd.backlight, lcd.nobacklight, lcd.home, and lcd.createChar for the custom character use. So moving on to the next slide. Next, we look into LM35 and LDR. The LM35 is a precision centigrade temperature sensor whose output voltage is linearly proportional to the temperature in degrees Celsius. Specifically, the scale grade is 10 microvolt per 1 degree Celsius rise in temperature. For example, if the temperature is 25 degrees Celsius, the output is about 250 microvolts. So, how it works in our system? We connect LM35 output to one of the Arduino's all analog input pins, for example A0. Arduino's built-in ADC reads the analog voltage and converts it into a digital value. For example, from 0 to 1000 naught to 23 for a 10-bit ADC. Then we convert the ADC value into voltage and then into temperature using the formulas. For example, for voltage is equal to ADC value into voltage reference or reference voltage divided by 1024. Then the temperature in degrees Celsius, temperature is equal to voltage divided by 10 meter volt per degree Celsius. That is, the voltage in microvolt is divided by 10. So in our project, we read the temperature, display it on the CLCD, and decide whether to turn the heater or cooler on or off based on the thresholds. Then we can look for the LDR. So what is an LDR? An LDR changes its resistance according to the ambient light. So more light, lower resistance, less light, higher resistance. By forming a voltage divider with LDR plus fixed resistor, you can obtain a voltage signal that varies with the light level. So how it's work in our system? So LDR output in our circuit is read by Arduino's analog input through the voltage divider. ADC reads the analog voltage representing light intensity with a higher voltage indicating more light depending on the design. Then we use that value to control the brightness of a LED or light using PWM. For example, if the sunlight is high, then LDR voltage will be high and ADC value will be also high. Then the garden light should dim or turn off. So if the sunlight is low, so ADC value will be low, then it decided to garden light on or brighten more. So PWM or pulse width modulation is used to control the average voltage or current to the load, for example, LED or lamp, through changing duty cycle. In our home automation system, the LED reading triggers automatic brightness control of the garden light. So moving on to the next section. In this section, I will explain how we configure Blynk platform for our home automation project. So what is Blynk? Blynk is a comprehensive IoT platform that includes a mobile application and a cloud service designed to allow users to quickly build interface for controlling hardware project and visualizing sensor data from anywhere in the world. It provides a drag and drop interface for creating custom dashboards on smartphones or web browser. Widgets such as buttons, sliders, graphs, gauge, and more make it possible to create the front end of your IoT system with minimal code. So Blynk supports many hardware boards like Arduino ESP32, etc. Multiple connectivity options like Ethernet, Wi-Fi, cellular, and allows you to send or receive data between hardware and a mobile device through the cloud. For our project, using Blynk means we can monitor temperature, light level, water tank level, and control devices like valves, heater or cooler remotely from our phone itself. So here is the sequence of steps to configure Blynk for our device. So the first step is to create a template. In the Blynk console, you create a template which describes a kind of device or like its data stream, metadata, or widget. So multiple devices of the same type can share the configuration. Then add first device. Within that template, add a specific device, for example, home automation node 1, and assign it to credentials like authentication token so your hardware can connect to the Blynk cloud. Then the third step is to set up data stream. It defines the flow of data you will send or receive from the hardware. For example, temperature reading, water reading, light level reading, control command for valve or light. These data streams map to the virtual pins in the code. Then the fourth step is in the developer zone. In the developer zone, there is an option called add widgets. So in the mobile app, you can drag and drop widgets. For example, gauge for the temperature, slider for the brightness control, switch for light on or off function, and then connect each to a virtual pin corresponding to your data stream. Then the last and fifth step is to connect the virtual pins. Each widget you add is mapped to a virtual pin, for example, V0, V1, V2, etc., which is your Arduino code will read or write using Blynk function. So the key Blynk functions we used in our code is first one is blynk.begin of auth, SSID or pass. This is used to initialize the connection between your board, Wi-Fi or other connectivity and the Blynk cloud via the given authentication token. Blynk.run. It is called inside the loop function to handle the Blynk background tasks like maintaining connection, process incoming commands, dispatch outgoing data. Then blynk.virtual write of vpin comma value or blynk.write. So depending on the version, we can use the two of them. It is used to send a value from your hardware to the widget that map to the virtual pin. For example, sending temperature reading to the mobile gauge. So these functions allow our automation system to integrate with the Blynk and enable remote monitoring and control. So that's it.
Now, we are moving on to our project implementation phase and along with a demo of what we have studied and done through our
For
internship journey.
showing the project demo, we are opening the PICSimLab Simulator. We have got the Arduino and we are going to select the spare parts which is already been organized. This is the LDR sensor and this is the LED associated with this. This is the temperature system that we got from the others option. We have next we have the Ethernet module. We also have the CLCD that shows the temperature here. Next we are going to get the tank, serial tank. Next we have to configure the serial port to COM2. We have already configured the Arduino to the COM1, so we have to facilitate the serial communication by configuring the serial tank to COM2. Now we haven't started the Blynk. While opening the spare part, it is showing the home automation project in the CLCD initially, and after that the temperature is been showing in the CLCD. Now our Blynk app is not activated yet. Now we are testing the LED by adjusting the value of LDR. can see that the LED brightness is adjusted by adjusting the LDR value. I'm just resetting the board once again and starting the spare part again. Now it's been showing the home automation project initially in the CLCD, and after that, after a certain delay, there would be, now initially the LED is off, and now the temperature value is been showing in the CLCD. Now the LED brightness is being adjusted according to this LDR value. The code has been already, the .hex file has been already loaded to the board, and we have connected now the serial tank to the board. Now the connection is all done and it is working clearly. Now I am making the inlet valve on in the Blynk app in my phone. In the serial tank, the inlet valve is opened and water is flowing inside the tank, and it is showing clearly the volume and inlet all on in the CLCD. And coming to the LDR, while adjusting the LDR values, the LED brightness also been adjusted accordingly. Now I am going to off the inlet valve through my Blynk app in my phone, and you can see the inlet valve has been get off in the serial tank. Next I am going to on the outlet valve in my Blynk app in my phone, and it is clearly showing the outlet valve off in the CLCD and the current volume in the CLCD. And while coming to the temperature system, I have been on the cooler, and the fan is been rotating now, and now I have on the heater, and the rotation of the fan has been stopped, and the temperature is been increasing as the heater is now on. Now the heater has been off through my Blynk app, and when the cooler is on, the fan again starts to rotating and the temperature falls down. The inlet valve, outlet valve, cooler and the heater all has been controlled through the Blynk app. Here all three requirements has been satisfied. First, coming to the LDR and LED, garden light control. The brightness of the LED has been controlled by the value of LDR. And next, coming to the temperature control system, when the cooler is on, the fan is rotating, and the temperature is being updated in the CLCD and also in the Blynk app. When the cooler is off and the heater became on, the temperature has been increasing, and it is clearly showing in the CLCD and also in the Blynk app. And the heater on off, cooler on off condition also has been showing in the CLCD clearly. Now coming to our last requirement, serial tank control. When I am clicking the button inlet on in my Blynk, the inlet valve has been on. Now the inlet valve is off and the outlet valve has been on in the Blynk app, and the water is flowing out from the tank and the volume is been reducing. That is clearly showing in the CLCD. Now the inlet valve has been on through the Blynk app. So this is the project implementation that we have successfully implemented as a part of this internship?